For part two of the serialization discussion, let's detour a little bit and talk about something called Endianness. As we said before, serialization is taking a whole block of data and pushing it down through the wires byte by byte or even bit by bit. We had floats and integers and things that take up more than 1 byte each, but we have to send them through here 1 byte at a time. Now that gives us two options for how we send those bytes. Should we send the least significant byte first, or should we send the most significant byte first? Obviously, those are two options. Take a moment to think about which one do you think makes more sense to you. In what we call the little endian system, we store and send the least significant byte first. And most modern hardware uses this system. However, there are systems that use big endian, which is when we store the most significant byte first. Examples of those might include a PowerPC or an old Xbox 360 or PS3 system. Let's see how that looks different in memory. Consider the integer number in hex 1, 2, 3, 4, 5, 6, 7, 8, stored as a 4-byte integer in memory. With a little endian system, we take the least significant byte and put it in the lowest memory address. So consider we're at this memory address. The least significant byte would be in that address. The next byte goes into the next address. And the 3, 4 goes into the next address. The 1, 2 goes into the fourth memory address. However, in a big endian case, what we're going to do is go the opposite direction. We're going to still stay at that same address and take these same 4 bytes, but we're going to store them in the opposite order. So first we store the most significant byte, the 1, 2, then the 3, 4, the 5, 6, and then the 7, 8. If we go into the debugger and look at a memory window, we can see what a number like this will look like. When viewed as a 4-byte integer, we see the number exactly like we typed it, in hex 1, 2, 3, 4, 5, 6, 7, 8. However, when you switch that view into 1-byte integers, looking at them a byte at a time, we'll see the endianness revealed, where the lowest memory address, E0, has the least significant 7, 8. So the number in this case looks like it says 7, 8, 5, 6, 3, 4, 1, 2. So which endianness is this system? Of course, that's a little endian system. The least significant byte is in the lowest memory address. And of course, the memory addresses increase as you go from left to right. So now, from a developer's point of view, which system would you say makes more sense and why? There's no wrong answer on this. If you spend a lot of time looking at memory windows, as I do, I think you might agree that looking at these little endian numbers can do a number on your head. On the other hand, I think it makes a lot of sense to say we should send the least significant byte first. And ultimately, as you can see, most modern systems have gone that way, indicating that the little endian systems seem to be the favorites. Let's look at the memory window in the debugger so you can see how this actually works. Put a breakpoint, and so when we launch the project, it'll stop right there. And I have my various windows, my call stack and my watch window, autos window. Let's look at some data. I've got vert here. Let's look at vert. I'm going to drop that in the watch window. And we can look at what the data is. We can also take the address of that, address of vert, and I'll just grab that address right there. And let's take a look at that in a raw memory window. This is where we find those debug windows, memory, and then you can have up to 4 of them. And let's just move the dock to there. So we have it side by side. You can put that anywhere you want, doesn't really matter. This is a raw memory window, and I want to look at this address that I have pasted right there. I could also just type right in here address, you know what, just vert will do it. Right? Or address of vert 0, right? That'll take me to that address and fill it in for me. Okay, this is the raw memory window looking at this data right here. So this is the data 0.50, and we see that displayed here. And then we see a bunch of C. That's how Visual Studio or this compiler fills in the memory that you're not using. It marks it for you. That's a good indicator that that hasn't been written to yet. It's uninitialized. So let's look at this in different modes. This is in 1 byte mode. If we right click here in this window, we get our options for how to look at the data. We're in 1 byte integers. We can look at it as 4 byte integers, and then it combines them, still in hex, but 4 bytes at a time. Right? And then we say, oh, but this is actually float data, as you can see, so we can display it as float data. So that's your memory window. It allows you to just look at whatever is in the memory at any given time. This shows you the address for this line where this starts. That's the address of this byte here. Put it back in 1 byte mode. That's the address of this first byte, and then we'll increase 1 byte at a time as you go across there. This over here, this gobbledygook on the right, this is interpreting these bytes as ASCII. And if it doesn't have an ASCII character, it just puts a dot. So there's a question mark right there. So 3F, that's this, is the question mark. Okay. What else do I want to show with this right now? Oh, I wanted to show the Endianness. Let's go back to 4 byte integer mode, and you can actually type in here to edit what is in the memory. So I've edited what's in the memory. I've put a number in there. It shows it as red that I've changed it. And you can see now some of those digits are corresponding to ASCII characters. Let's see that as 1 byte integers, and we'll see that it has taken let's go back here, the least significant byte is 7/8, right? The most significant byte is 1/2. And it has put the 1/2 here and the 7/8 here. So we are going in order of address, we're increasing from the minimum address here. So the minimum address has that least significant 7/8 in it. See that again, the 7/8. And but it does cause it to reverse the direction. Now notice, we'll talk about this more again in the future, but as long as I did this, take a look at what has happened to my position. By putting this value in, it has affected how that's interpreted as a float. And that's a gibberish number. We'll want to put that back. So let's just put it back. I can put it back here. As long as we're here, one more thing to look at is these CCCs. What do those look like as floats? Because we figured out this was float data. If we look at it as float data, you'll see it's interspersed with this weird number. It's a legal float, but it's a weird float. It's not something you expect to see repeated throughout your game. It's not like a commonly used game number. And that's a tip that maybe you're looking at it in the wrong mode. You can, boom, look at it in this mode, and you'll see what it is. All right, and then you say, oh, I know what that is. Okay, that's the memory window in the debugger. Most systems these days are a little endian. But what do you do if you've got to maintain compatibility with a big endian system? I encountered this myself when trying to port some code from PS3 to PS4. The PS3 was big endian, PS4 was little endian. So what do we do about that? What you do is you decide up front which endianness your data stream is going to be and remain consistent with that always. So little endian being the more common these days, I would suggest little endian for your data streams. So if you do have a big endian system somewhere participating in this data stream, it will be the responsibility of that system to correct all of the data coming in and going out of that. So when you write your data, make sure you always write your data in the little endian format. So if you have a big endian system, you will need to swap the order of the bytes before you write them out. Likewise, when you read them in, you'll know that you have read them in the wrong order, and so you will read them in and then swap the order of the bytes again. The thing about Endianness is that this only applies to multi-byte data. If you're writing out characters, then they go out 1 byte at a time naturally. So there's no swapping necessary. But a float, for example, is 4 bytes. The order of those 4 bytes is what we're talking about. That means it's going to depend how big your data is when you're trying to decide how many bytes need to be swapped. And you do it at the atomic level, at the level of an individual data element. What do I mean? Consider this. Perhaps you have a uint 16 bits as an integer. That's 2 bytes. So those 2 bytes need to be swapped. On the other hand, maybe you have a 4-byte integer. 4-byte integer, or perhaps a float. A float is also 4 bytes. Those 4 bytes need to have their order swapped. Or perhaps your data is even bigger. Maybe it's a 8-byte piece of data, like a uint 64, for example, or a double precision float. That would be 8 bytes that need to have their order reversed. Let's do an example. Consider the example of a 2-byte integer, OX1234. Hexadecimal is very convenient because it's super easy to turn that into binary. Each digit is just 4 binary bits, starting with the 1, 0, 0, 0, 1. And then the 2, 0, 0, 1, 0. The 3, 0, 0, 1, 1. And the 4, 0, 1, 0, 0. That's our original data. Let's next look at this. This symbol here is the shift left operator. It doesn't mean send something to a data stream. Turns out in your very first C++ class, when you learned that's how you write something to the command line, you were using an overloaded operator. No one had taught you about that yet. It took us a while to get to that. Now we see that's actually the arithmetic shift left operator. It means take the bits and push them to the left by 8 digits. So 8 binary bits are shifted to the left. This 0 will be moved to the left to this position here. 0, 0. This 1 moves to the left by 8, 0. 1, 1, 0, 0. So these 8 bits here are shifted to the left 8 positions. And we're going to fill in from the left. We're going to fill in with zeros. All right, so that's that one. How about this? This is the shift right operator. So we're going to take the original number and shift it to the right by 8 bits. So let's start here. This 0 goes to the right 8 places, so it goes here. 0, 0, 0, 1. Now we're here. 0 goes to the right 8 places, that's here. 0, 0, 1, 0. All right, now, what do we fill in from the left-hand side? This one's a little bit tricky. If we say the data is unsigned, which we have said here is unsigned, that means that the most significant bit that we're filling in here is always 0. If we had said that was a signed integer, then we would copy the most significant bit on down in order to maintain the sign of the original value. We've said unsigned, so we'll just fill it in with zeros. We've got 8 of those. And the next instruction is to OR those together bit by bit. So we're going to OR those two together. 0 or 0 is 0. 0 or 1 is 1. 0 or 0, 0. 0 or 1 is 1. 0, 0, 0. 0, 0, 1, 0. 1, 1, 0, 0. Back into hex, what have we got? 3, 4, 1, 0, 0. 3, 4, 1, 0, 0. 3, 4, 1, 0, 0. 3, 4, 1, 0, 0. 3, 4, 1, 0, 0, 0. 3, 4, 1, 0, 0, 0. 3, 4, 1, 0, 0, 0. 3, 4, 1, 0, 0, 0, 0. 3, 4, 1, 0, 0, 0, 0. 3, 4, 1, 0, 0, 0, 0. 3, 4, 1, 0, 0, 0, 0, 0. 3, 4, 1, 0, 0, 0, 0, 0. 3, 4, 1, 0, 0, 0, 0, 0, 0. 3, 4, 1, 0, 0, 0, 0, 0, 0. 3, 4, 1, 0, 0, 0, 0, 0, 0, 0. 3, 4, 1, 0, 0, 0, 0, 0, 0, 0, 0. 3, 4, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 2. We have successfully swapped the bytes. The 4-byte swap is a little bit more complicated. It involves the same instructions, some shifting to the right and ORing the results together, but also we're using an AND operator to mask off only the byte that we're looking for. So individually, we'll select the byte that we want out of it and move it to the spot that we want it in, and then we'll OR all those 4 combinations together. And here's the 8-byte swap, which takes a few more instructions, but it's the same basic idea. I've shown some math now of how to swap bytes, but I didn't say which way this goes. Remember, you have to swap bytes from little endian into big endian, and then when you write the bytes back out, you have to swap them again from big endian into little endian. Which one is this? Think about that for a moment. Is this the little to big conversion, or is this the big to little conversion? If you said it's both, you got the right answer. Swapping bytes is the same. If you swap bytes once and then swap them again, they're back to the way they started. So reversing the order doesn't matter which way you're going. You'll use the exact same math functions to swap the bytes, whether you're going from little to big or from big to little. Let's call that the end of this video, and I'll see you again in part 3.